Welcome to this coding walkthrough. Today, we'll be tackling LeetCode problem number 1672, titled Richest Customer Wealth. In this problem, our goal is to determine the maximum wealth among all customers based on their respective accounts. We'll explore the solution step by step, so let's get started. In this problem, we are working with a grid accounts that represents the wealth of multiple customers across several bank accounts. Each row in the grid corresponds to a customer, and each column represents a specific bank account. The value accounts, I, J, indicates how much money the ITH customer has in the JTH account. Our task is to determine which customer is the richest by calculating the total wealth for each customer and finding the maximum among them. Customer wealth is defined as the sum of all the values in their row. The final goal is to return the maximum wealth across all customers. For instance, in the first example, we are given accounts equals 1, 2, 3, 3, 2, 1. Here, customer 0 has a total wealth of 1 plus 2 plus 3, which equals 6. Similarly, customer 1 has a total wealth of 3 plus 2 plus 1, which also equals 6. Since both customers have the same wealth, the richest customer wealth is 6. In another example, if accounts equals 1, 5, 7, 3, 3, 5, customer 0 has wealth 1 plus 5 equals 6. This time, customer 1 has wealth 7 plus 3 equals 10, which is the highest total so far. Customer 2 in the same example has a wealth of 3 plus 5, which equals 8. Comparing all three customers, the highest wealth is 10, so we return 10 as the richest customer wealth. In a third example, we have accounts equals 2, 8, 7, 7, 1, 3, 1, 9, 5. Customer 0's wealth is 2 plus 8 plus 7, which is 17. Customer 1 has a total of 7 plus 1 plus 3, which is 11, and customer 2 has 1 plus 9 plus 5, totaling 15. Among these, the richest customer wealth is 17. Now, let's look at the constraints. The number of customers M can range from 1 to 50, and each customer can have between 1 and 50 bank accounts. The wealth in each bank account, accounts I, J, will always be between 0 and 10,000. This means the grid size and individual values are within manageable limits. For edge cases, consider when there is only one customer with one account, such as accounts equals 5. Here, the wealth is simply 5. If all customers have 0 wealth, like accounts equals 0, 0, 0, 0, 0, 0, the richest wealth is 0. Lastly, at the maximum grid size of 50x50 with all accounts at 10,000, the richest wealth would be 500,000. These constraints and examples give us a clear understanding of the problem's scope and edge cases to consider. To solve the problem of finding the richest customer wealth, we begin by understanding the structure of the input. The grid accounts, I, J, represents the amount of money the ITH customer holds in the JTH bank account. Our goal is to determine the customer with the maximum wealth, where wealth is defined as the sum of all their account balances. One straightforward way to solve this is through the brute force approach. Here, the intuition is simple. For each customer, compute the sum of their bank balances, compare it to a running maximum, and update the maximum if we find a larger value. The algorithm involves initializing a variable max_wealth to 0, iterating over each row of the grid, calculating the sum of balances for each customer, and checking if this sum exceeds the current maximum. At the end of the process, we return the largest wealth value. This method is easy to implement and provides a clear solution to the problem. Analyzing the brute force approach, its time complexity is O, M*n, where M is the number of customers and N is the number of bank accounts per customer. This is because we must iterate through every element in the grid to compute the required sums. The space complexity, on the other hand, is O(1), since no additional memory is used beyond a few variables for the computation. Now, while the brute force approach is efficient for this problem, we can make the implementation more concise and readable by leveraging Python's built-in functions. Using an optimized approach, we can utilize map to calculate the sum of each customer's bank balances and max to determine the largest value directly. This approach simplifies the code while preserving the same functionality. The algorithm involves applying map, sum, accounts, to generate a list of customer wealth values and then using max to find the largest wealth. Finally, we return this maximum value, achieving the same result with less manual iteration. The optimized approach using Python's built-in functions retains the same time complexity as the brute force method, which is O(m*(n). This is because the sum function iterates through each customer's accounts, and max subsequently processes the resulting list of sums. However, the space complexity increases slightly to O(m), because map sum accounts generates an intermediate list of customer wealth values, where m represents the number of customers. Another alternative to consider is the row-wise reduction technique. Here, instead of creating an intermediate list, we compute the sum of each customer's accounts on the fly and maintain a running maximum. This approach avoids additional memory usage since it does not store intermediate sums. The algorithm involves iterating through each row, calculating the sum dynamically, and updating the maximum wealth as needed. By the end, the maximum wealth is returned. This method is conceptually similar to brute force but avoids explicit storage, making it slightly more space efficient. When comparing the different strategies, there are several trade-offs to consider. The brute force approach is simple and intuitive, making it easy to understand and implement. However, the optimized method using map and max improves code readability and conciseness, which can be beneficial in collaborative or production environments. The reduction technique, while similar to brute force, avoids storing intermediate sums, making it slightly more space efficient. In terms of space complexity, both the brute force and reduction approaches use O(1) space, while the map approach requires O(m) space due to the intermediate list of sums. Performance-wise, all approaches share the same time complexity of O(m*(n), so the choice ultimately depends on clarity and memory usage. For this problem, the recommended strategy is the optimized approach with map, sum, accounts, and max, as it is concise, leverages Python's built-in tools effectively, and is well suited to the problem's constraints. That said, the brute force method is also a valid choice, particularly in languages without functional programming utilities like map. To solve the problem of finding the richest customer wealth, we start by understanding the given inputs and the expected output. The input is a 2D list called accounts, where each row represents a customer and each column within that row represents the balance in one of their bank accounts. Our task is to calculate the total wealth for each customer by summing up all the balances in their row, and then identify the maximum wealth among all customers. For example, if there are 3 customers and each has accounts with different balances, we need to determine which customer has the largest total sum and return that value. This is a straightforward problem that involves iterating through the rows of the 2D list, summing up the balances for each customer, and keeping track of the highest sum encountered along the way. Now, to determine the maximum wealth, we employ a systematic approach. First, we initialize a variable called max_wealth to 0. This will be used to track the highest wealth as we iterate through the customers. For each customer, we calculate their total wealth by summing up all the elements in the row that corresponds to their accounts. We then compare this calculated wealth with the current value of max_wealth. If the customer's wealth is greater than max_wealth, we update max_wealth to reflect this new highest value. After processing all the rows, the value stored in max_wealth will represent the maximum wealth among all customers. This approach ensures that we only traverse the grid once, making it efficient with a time complexity of O(m*(n), where m is the number of customers and n is the number of accounts per customer. Additionally, we must consider edge cases, such as when there is only one customer with one account, to ensure our algorithm is robust. Additionally, the problem constraints simplify our implementation. Since the input grid will always have at least one customer and one account, we don't need to handle empty inputs. To optimize our solution, we can use Python's built-in sum function to calculate the wealth of each customer efficiently, reducing code complexity. Regarding data structures, the 2D list accounts serves as the input, where each row represents a customer's accounts. 2 primary variables are used, max_wealth, which keeps track of the highest wealth encountered, and a temporary variable, such as current_wealth, to store the sum of a customer's row during iteration. The pseudocode for this approach is straightforward. We start by initializing max_wealth to 0, then iterate through each row and accounts, compute the row sum, and update max_wealth as needed. Finally, we return max_wealth after processing all rows. This method ensures clarity and efficiency. The pseudocode for the solution concludes with returning the value of max_wealth after processing all rows. The time complexity of the algorithm is O(m*n), as we calculate the sum of each row, which takes O(n) time, and repeat this for all m rows. The space complexity is O(1), since we only use a constant amount of extra space, regardless of the size of the input. Let's illustrate the solution with an example. Suppose the input is a 2D list where accounts equals 1, 2, 3, 3, 2, 1, 4, 5, 6. Here, each row represents the account balances of a customer. We will calculate the total wealth for each customer and determine the maximum value among them. This step-by-step walkthrough demonstrates how the algorithm processes the data to arrive at the correct result. In the example execution, we start by initializing max_wealth to 0. For the first customer with accounts 1, 2, 3, we calculate their total wealth as 6. Since 6 is greater than the current max_wealth of 0, we update max_wealth to 6. Next, for the second customer with accounts 3, 2, 1, their total wealth is also 6. However, since it is not greater than the current max_wealth of 6, no update is made. Finally, for the third customer with accounts 4, 5, 6, their total wealth is 15. This is greater than the current max_wealth, so we update max_wealth to 15. After processing all customers, the algorithm returns max_wealth, which is 15. This value represents the maximum wealth among all customers, and it matches the expected output. This implementation solves the richest customer wealth problem by determining the maximum wealth among all customers in a 2D list of accounts. Here's a step-by-step explanation of the code. 1. Class definition. We define the solution class, which is standard for LeetCode problems. 2. Function definition. The maximum wealth function takes one parameter, accounts, which represents the 2D list where each sublist corresponds to a customer's bank accounts and their respective balances. 3. Initialize maximum wealth. A variable max_wealth is initialized to 0. This will keep track of the highest wealth found so far during the iteration. 4. Iterate through customers. A for loop iterates over each customer in the accounts list. Each customer is represented as a sublist of integers, where each integer denotes the balance in a specific bank account. 5. Calculate wealth. Inside the loop, the sum function is used to calculate the total wealth, sum of all bank account balances, for the current customer. 6. Update maximum wealth. An if statement checks if the calculated customer_wealth is greater than the current max_wealth. If so, max_wealth is updated to the value of customer_wealth. 7. Return the result. After iterating through all customers, the function returns max_wealth, which holds the highest wealth among all customers. ###example. If the input accounts is 1, 2, 3, 3, 2, 1, 4, 5, 6, the function will calculate wealth for the first customer, 1 plus 2 plus 3 equals 6. Calculate wealth for the second customer, 3 plus 2 plus 1 equals 6. Calculate wealth for the third customer, 4 plus 5 plus 6 equals 15. The maximum wealth is 15, which will be returned as the result. This solution has a time complexity of O(m*n), where m is the number of customers and n is the number of accounts per customer, as we iterate through all the elements of the 2D list. The space complexity is O(1), since no additional data structures are used. This Java implementation mirrors the logic of the Python solution for the richest customer wealth problem. It defines a method maximum wealth that iterates through a 2D array of customer bank balances, calculates the total wealth for each customer, and keeps track of the maximum wealth found. Key differences include Java-specific syntax, type declarations, and the use of standard for each loops to traverse arrays. In the richest customer wealth problem, the goal is to determine which customer has the maximum wealth by summing up the balances across all their bank accounts. The input is a 2D list called accounts, where each row represents the accounts of a single customer. For example, in the first example, we have two customers with accounts 1, 2, 3, and 3, 2, 1. To solve the problem, we start by initializing max_wealth to 0. Then, we iterate through each customer. For the first customer, 1, 2, 3, we compute their total wealth by summing up the values in their accounts, which gives us customer_wealth equals 6. Next, we compare this customer's wealth, which is 6, with the current value of max_wealth. Since 6 is greater than 0, we update max_wealth to 6. Moving on to the second customer, 3, 2, 1, we calculate their total wealth as well. Customer_wealth equals sum, 3, 2, 1, equals 6. Comparing this with max_wealth, we see that 6 equals the current maximum, so max_wealth remains unchanged at 6. At the end of this process, we return max_wealth, which is 6. This approach ensures that we correctly identify the maximum wealth among all customers. In a second example, the input is accounts equals 2, 8, 7, 3, 1, 9, 1, and we follow the same steps to find the richest customer. We initialize max_wealth to 0 again. For the first customer, 2, 8, their total wealth is customer_wealth equals 10. Since 10 is greater than max_wealth, we update max_wealth to 10. The second customer, 7, 3, also has a total wealth of customer_wealth equals 10. In this case, since 10 is equal to the current max_wealth, we do not update it. For the third customer, 1, 9, 1, we calculate their wealth as customer_wealth equals 11. Since 11 is greater than the current max_wealth of 10, we update max_wealth to 11. After processing all customers, the maximum wealth is determined to be 11, which becomes the final output. In an edge case where there is only one customer, such as accounts equals 5, 5, 5, 5, we still follow the same procedure. We initialize max_wealth to 0. For the only customer, 5, 5, 5, 5, we calculate their total wealth as customer_wealth equals sum, 5, 5, 5, 5, equals 20. Comparing this with max_wealth, we find that 20 is greater than 0, so we update max_wealth to 20. Since there are no other customers, the maximum wealth remains 20, which we then return as the result. This example highlights how the algorithm handles cases with a single customer efficiently. The solution systematically iterates through each customer, calculating their total wealth using Python's built-in sum function. By comparing each customer's wealth against the current maximum, the algorithm ensures that the richest customer is identified accurately. This approach processes every customer exactly once, making it both simple and efficient. The time complexity of this solution is O(m*n), where m is the number of customers and n is the average number of accounts per customer. The space complexity is O(1), since we only use a single variable, max_wealth, to track the maximum value. This method ensures optimal performance while adhering to the problem's requirements. To analyze the time complexity of this solution, we first define the variables. Let m represent the number of customers, which corresponds to the rows in the accounts list, and n represent the average number of banks per customer, or the columns in each row. The algorithm begins by iterating through each customer in the accounts list, resulting in O(m) operations. For every customer, it uses the sum function to calculate the total wealth by adding up their account balances. Since the sum function processes all n accounts for a customer and each addition is a constant time operation, its complexity is O(n). When we consider all customers, the total time complexity becomes O(m*n). This is because the outer loop runs m times, and for each iteration, the inner sum function runs n times. Mathematically, this is expressed as O(m*n), which simplifies to O(m*n). Now let's look at the space complexity of the solution. The algorithm uses only a single integer variable, max_wealth, to store the maximum wealth encountered so far, which requires O(1) constant space. Additionally, the sum function calculates the total wealth for each customer directly in place. It doesn't allocate memory proportional to the input size, and the intermediate result is stored in the customer_wealth variable, which also takes up O(1) space. Importantly, the input list accounts as read-only in this algorithm, meaning it doesn't contribute to the space complexity. Therefore, the overall space complexity of the solution is O(1), making it very efficient in terms of memory usage. When comparing this solution to a brute force approach, the efficiency becomes even more evident. A naive method might involve generating all possible subsets of accounts and summing their values to find the maximum wealth. This would result in an exponential time complexity of O(2)(m*(n), which is computationally impractical for large inputs. In contrast, the current solution directly computes the sum for each customer in O(m*(n) time, making it far more efficient. Additionally, the time complexity remains O(m*(n) in all scenarios, best case, average case, and worst case, because the algorithm always processes all rows and columns regardless of the data. No shortcuts or additional computations are introduced based on the input values, further reinforcing its consistent efficiency. The time complexity of O(m*(n) is rooted in the algorithm's nested iteration structure, where the outer loop processes m rows, and the inner operation, the sum function, processes n columns per row. This ensures that each element in the input list is accessed exactly once, with no redundant or overlapping calculations. Similarly, the space complexity of O(1) is justified by the absence of additional data structures like lists or dictionaries to store intermediate results. The algorithm relies solely on a fixed number of variables, making it both time and space optimal for the problem constraints. In summary, this solution strikes a balance between simplicity and efficiency, addressing the problem requirements in an optimal manner. When solving this problem, there are several common mistakes to watch out for. First, it's important to account for edge cases, such as when there is only one customer or only one bank account. For example, if the input is accounts equals 5, your solution should correctly handle this minimal case and return 5. Another area to be cautious about is handling empty or invalid inputs gracefully. Although the problem guarantees valid input, it's good practice to consider scenarios like accounts equals in real-world applications. Additionally, many people confuse rows and columns in 2D arrays, which can lead to summing across the wrong dimension and incorrect results. Always ensure you're iterating over each customer's accounts, which corresponds to summing the rows. Lastly, while nested loops can work, they're often unnecessary. Python's sum function, or equivalent methods in other languages, lets you simplify your code and improve efficiency without needing explicit double loops. Another common mistake is writing overly complex solutions that sacrifice readability. Simpler code is not only easier to debug but also helps in showcasing your understanding during interviews. Strive for clean, efficient solutions that are easy to follow. Now, in an interview setting, clarity and consideration of edge cases are crucial. Start by discussing the problem constraints and potential corner cases with your interviewer to demonstrate your thought process. As you write your solution, take time to explain your approach and any trade-offs you considered. For example, if you chose to use built-in functions, highlight how they contribute to both simplicity and performance. Additionally, always be ready to discuss time and space complexity. For this problem, the time complexity is O(m*(n), where m is the number of customers and n is the number of accounts per customer. This is optimal given the constraints, so ensure you communicate that effectively. This problem has real-world applications, such as analyzing customer data in banking or e-commerce to identify top clients based on their total wealth. Drawing these connections can help you better understand the relevance of the problem and discuss its practical use in interviews. For related problems, LeetCode 239, Sliding Window Maximum, also involves finding maximum values but focuses on a dynamic sliding window instead of summing rows. LeetCode 54, Spiral Matrix, challenges you to traverse a 2D array in a custom pattern, which tests similar skills in matrix manipulation. Additionally, LeetCode 566, Reshape the Matrix, deals with reshaping a 2D array, and LeetCode 48, Rotate Image, involves transforming the matrix in place. These problems share underlying concepts with the Richest customer wealth problem, and practicing them can strengthen your understanding of 2D array operations. Finally, let's consider alternative approaches and their trade-offs for solving this problem. A brute force approach involves using nested loops to manually calculate the sum of each row and track the maximum. While this is straightforward and easy to implement, it's less efficient and can make your code harder to read compared to other methods. A more optimal approach is to use built-in functions like Python's sum to calculate the row sums. This method is concise, highly efficient, and improves code readability. However, in an interview, it may not fully demonstrate your understanding of the underlying logic, so be prepared to explain the trade-offs. For larger datasets, you might consider Python libraries like NumPy, which enable efficient, vectorized operations. While NumPy is powerful, it requires additional imports and can be overkill for simple problems like this. However, it's a great choice in high-performance scenarios where efficiency is critical. Great job on completing this problem. To summarize, we calculated the maximum wealth across customers by iterating through their account balances and keeping track of the largest sum. This problem highlighted the importance of basic array operations and reinforced clean coding practices. Thanks for watching, and make sure to like, subscribe, and stay tuned for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!